Right?
Yeah.
Wonderful. That's a quick Facebook. I have the issue of Twitter. Yes, so then you like. Okay. Thank you so much. All right. Thank you for putting up with the technical difficulties, and thank you all for coming out here today. So we have 4 talks. I'll be presenting a quick introduction to what DeepChem is and how to use graph convolutions, one of the most interesting technologies in DeepChem. So we followed up by Peter Eastman, who will be talking about all the new reinforcement learning things you can do. So if you thought that chemistry and playing video games had nothing to do with each other, you're in for a surprise and treat today. After that, we'll have a short break, and then we'll have Jocelyn will be giving a talk about doing protein ligand binding affinity prediction with 3D COMNETs, not using DeepChem, but using other cool technology from her group, David Koh's group at CMU University of Pittsburgh. And we'll have Brian Naughton, who will round it out by talking about computational methods for biology. And let's get started. So maybe the first question is, for those of you who haven't actually used DeepChem before, what is it and why should you care about it? The shortest answer is DeepChem is a system for doing molecular machine learning. So what is molecular machine learning? You can say that most computer machine learning work is, say, done on natural language processing, done on computer vision, done on, say, the types of things, the skills you learn in kindergarten. So a lot of machine learning work is really attempting to take those like visceral skills we've mastered before 5, say balance, speech, understanding, reading. With molecular machine learning, we're rather trying to say, move that up to doing things we, say, learn in grad school or undergrad. That is, given experiments where you have various molecules that you test, and you have different properties of these molecules, can we learn a system that predicts the properties of new molecules and tells us things about them? So why is this something we should care about? Maybe one of the best ways to demonstrate this is by looking at all the different things we use molecules to do. So here's a short summary of the sort of things that we use molecules to do. This work is from a dataset collection called MoleculeNet, and by Michael Liu, who just entered the room. The goal of these types of collections is to show that you can use, say, molecular machine learning toolkits to answer questions in quantum mechanics. You can address problems in physical chemistry, say things like solubility or melting point. You can begin to address problems in biophysics. How does a particular molecule interact with other molecules that might be biologically important? You can go all the way up to physiology. It turns out that we take in all types of molecules. We call some of them food, we call some of them medicine. But in some sense, they all go through the same digestive system. So we can use molecular machine learning techniques to get a handle on a very vast array of fields. So part of the reason you should use DeepChem is if you care about one of these downstream applications and you have moderate amounts of data, let's say a few hundred data points even, you can begin to do machine learning with your data and answer useful questions. So I know some of you are from, say, academic labs. You can probably use tools like DeepChem to write research papers. If you're from companies and you want to design molecules that do something interesting, you can use DeepChem to help you design those molecules. If you're from a solar cell company and want to, say, create new higher efficiency solar cells, again, these are probably the types of tools that can help you. So my hope is that there will be something here for all of you. And we've done a lot of work, especially Carl Leswing, who is in Boston and couldn't be here, and Peter, and in making DeepChem easy to install. So the hope is that after you listen to our talks, you'll be inspired to go kind of install it. It's a standard Python Anaconda install, if you're used to Anaconda Python. Or there's a couple other installation routes, depending on what you like. Play with some of the examples, play with the Python notebooks, and get a sense for what this tool is and what it can do for you. So with that, I'll start talking about some of the more interesting tools that we have in DeepChem. So one of the most fundamental primitives for working with molecules is something called a graph convolution. the idea is that in regular computer science, there's a lot of importance to doing something that is called a convolutional neural net. This is the fundamental technology that's used for computer vision. That is, given an image, you want to classify who's in this image, what's in this image, where is it, self-driving cars. All of these are convolutional neural nets. And the basic idea of a convolutional neural net is there's something called a local receptive field. This is taken a concept from biology. It's the part of, say, our body or stimuli that a neuron in our brain responds to. Similarly, in convolutional neural nets, you have a little patch of an image, and that's the stimuli, the local receptive field that artificial neuron responds to. And you arrange these artificial neurons upwards in towers, and these form convolutional neural nets. Now, convolutional nets are very useful, but they basically require input to come in as a rectangle. Or you can view it as, say, a regular grid of pixels coming in. Now, for molecules, we all know that molecules don't come in regular grids. They're fundamentally irregular. Every molecule is its own shape, and a different grid, or a different graph, so to speak, is a different molecule. So how can we generalize the concept of a regular convolutional neural net to work on an irregular grid that, say, may form strange geometries? And kind of the basic solution to that is what's called the graph convolution. So a graph convolution is made up of various operations, again, to redefine the notion of a local receptive field. The idea is that maybe the local receptive field, so to speak, should be of an atom, should be all the other atoms that are bonded to it, or maybe the atoms that are bonded to that. It's a different notion of a local environment. Because the idea is that a convolutional network is really about saying, let's take local structure, let's integrate it together, and let's solve global problems. In images, it says, take local patches and answer questions about what's in a big picture. Similarly, you take local chemical environments of a molecule surrounding local atoms, and you answer global questions about the molecule. What is its solubility? What, say, is the melting point? What happens when I feed this to a healthy adult human being? All of these are questions you can begin to answer. So with graph convolutional networks, the basic idea is that you have, say, input in a molecule that you care about. And here's a very simple molecule kind of up there on that screen. And the basic idea is that for every atom in that molecule, you start with a local vector, a description of its chemical environment. So for those who are chemists, this might be things like hybridization properties. It might be things like the atomic type, or some other local descriptors of the chemistry. Basically simple off-the-shelf things that you can compute with very basic chemistry. Then you say you repeatedly apply these graph convolutional primitives. You can think of them as information transfer operators. So let's say at the very bottom, I only know about me. Then I have graph convolutional layers, and after I apply that, maybe one step in, I know about me and I know about my neighbors. 2 steps in, I know about my neighbor's neighbors, and so on and so forth. And at the very bottom, you do what's called a graph gather. You gather in all the local descriptors, you glue it together, and you have one vector that describes the entire molecule and its behavior. And you can use this learned vector, or this learned featurization, so to speak, to answer very interesting and quite useful questions about the behavior of molecules. So far, this has kind of been a pretty abstract, just kind of mathematical description. But now we'll go to a demo, not live, printed out, but one that you can actually try for yourself. One sec. This is an IPython notebook. For those of you who installed DeepChem locally, you can actually check this notebook out from the Examples Notebooks tab, and you can try running it yourself after our talk. And the idea is that I gave you a lot of high-level description about what a graph convolution is, but how can you kind of get into the nitty-gritty? How can you use one for yourself? So the first part is let's kind of walk through the notebook. So as in every Python package, the first step is you need to import a bunch of stuff. So we start by importing NumPy. That's kind of the standard toolkit in the Python data scientist toolbox. You start by importing TensorFlow as TF, and finally you import DeepChem as DC. And now, for people who are kind of new to GraphCon, we offer this bundling that's called the GraphCon TensorGraph. It is a graph convolutional network, kind of pre-wrapped out of the box, set with reasonable defaults that you can just import and begin to play with. So now we've kind of done our imports. The question is, what steps do we have to take before we can start to run these things? So the first thing we need before doing any machine learning, of course, is we need a way to get some data. So we've done a lot of work on MoleculeNet, a benchmarking system that gathers a bunch of data and puts it together. So if you want to use the MoleculeNet datasets, all you have to do is do this one simple call, dc.molenet.load whatever, and there's about 20 or 30 options. In this case, we want to load TOX21. For those of you who work with, say, chemical datasets, TOX21 is a very nice collection. It's about 10,000 compounds. It's done by the EPA and NIH. It's measured in about 12 assays for interactions with various nuclear receptors. The idea is that if you're interacting with a nuclear receptor, you will probably do not want that thing anywhere near you. So this is a nice gauge of toxicity. Now, of course, human toxicity is an extraordinarily complicated phenomenon. So you shouldn't trust, say, just as data. But if you're beginning to answer questions about, is this compound safe to be human? This isn't a bad first starting point. So now that we can just load this data up, we make this call to this load TOX21 function. We get back, say, the tasks. There's about 12 different experiments bundled up in this collection. We get back the data sets. And for those of you who've done machine learning before, you know you have a train split, you have a validation split, and you have a test split. This is kind of pre-bundled for you. And we have it all featureized. So the first step of any machine learning, of course, is to take in data, which can be something raw, something live, something measured, and transform it into vectors that we can understand. If you remember back to the graph plot, we had an initial vector on top of every atom in the molecule. This function, load TOX21, does that for you out of the box. If you notice, we set the featurization to read graph plot. There are some other variants, but this kind of does the first steps for you out of the box. And then you say, all right, now I have some data sets. What does it take for me to start training a model? So if you've ever used standard Python machine learning toolkits, things like scikit-learn or Keras, this should look very familiar to you. We make a model object. It's called a GraphCom tensor graph. We tell it how many different experiments we want to have processed. And we say, all right, process this in batch sizes of 50. Look at neural nets before. One of the common things about neural net training is you never look at all the data at once. You instead look at small batches at a time and train iteratively over these small batches. So we're looking at a batch size of 50, very standard, very normal number for kind of training these neural nets. And we say this is a classification problem. That is, these experiments have zeros and ones. Is this compound active against this nuclear NR-AR receptor? We don't have real valid outputs in the system, but if we wanted to, we change that to weight regression, and we can handle real valid data. And then we say, you know, model.fit, and that's it. With that, we have a basic model trained. On this 10,000 data set, 10,000 point data set, it only takes about 130 seconds to train on my dinky little laptop here. So for any chemical data set you have, unless you're running some very large high throughput stream, you probably don't even need custom hardware. Like, these things are pretty fast, they're pretty optimized. You should be able to train simple graph convolutional networks in a few minutes on very modest hardware. If you have a GPU, that would be great. This might actually not even speed up that much because there's GPU, CPU memory transfer. But if you happen to have millions of data points, you're so lucky, you might need to buy a $1,500 GPU. But the nice thing is there's not that much hardware requirements to start using these things. All you have to do is kind of make these calls from this fit, and you have a model. Now, we made a model, but we don't know anything about how accurate it is. So let's kind of dig into that. So we need to define a metric, a mathematical function that tells us how accurate the model we've created is. So the metric we're going to use is something called drop AUC. It's a measure of how accurate a binary classifier is. It's one of the standard things people measure when kind of getting a sense of, say, ad click rate uses drop AUC, for example. If Google wants to predict if someone is going to click this ad or not, +1, you'll use something like the ROC AUC score. Similarly, we're not Google, but we will use a ROC AUC score. And all you have to do is do a simple call to dc.metrics. If you use scikit-learn, this is like sklearn.metrics. And then you say model.evaluate, and then you pass in the data set and the metric. And there's this one thing I left out called transformers. It's the pre-processing steps you apply to the data set. So one kind of rule of thumb is neural nets are really finicky. Lots of need pre-processing in order to make things happen. DeepChem kind of does this for you out of the box. All you have to do is kind of pass along the transformations that were applied. And after that, we get a score out. So the score tells us, so for those of you who haven't seen ROC AUC before, 0.5 is random, 1.0 is perfect. The score on the train set should be pretty high, close to 1, because that's information we've already seen before. It's a score on the validation set that's a better measure of how accurate you are. And in this case, we see 0.9-ish on the train set. All right, it more or less memorized what we gave it. And then 0.8 on the train set. Not bad at all. That's enough to kind of tilt an experiment. If you have this It's not quite 80% accuracy, but that's a rough first order rule of thumb. System that tells you, it can give you a useful tilt if you apply this thing when you're beginning to say, design an experiment and you need to avoid things that are potentially toxic. So this is kind of neat. This is kind of 20 lines of code. This is enough to get you off the ground. But let's say you're an advanced user. You're saying, well, I don't know what's inside that GraphCon tensor graph. I want to make my own special GraphCon, which I think is going to be magical. How can I do that? The nice thing is that you can do this entirely in DeepChem's user space. So there's a very nice underlying primitive, a class called TensorGraph. The idea is that a deep network is nothing more than a sequence of tensor transformations. So for those of you who aren't physicists, a tensor is a generalization of a vector or a matrix. And you apply a sequence of these transformations in a computational graph, probably a directed acyclic graph for those of you who've done compilers or other toolkits. And the idea is that any sort of transformation you want to express, you assemble it in this tensor graph. So at the very bottom of the tensor graph, we put in inputs to the computation. These are the features. So in that beautiful two-line call, all this is kind of abstracted away underneath the hood, but it's kind of, we've taken it out and kind of put it out in public to see what's underneath the hood of the system. So what we do is we pass in multiple things. Remember, there's this local descriptor for every atom in a molecule. That's the atom features. If you want to express the topology of the molecule, that's done with something called an adjacency list. And you see these adjacency listings. There's a couple more bookkeeping primitives in here. It turns out that when you really get into the weeds, TensorFlow is actually pretty janky. There's a lot of pain you have to do in order to really make TensorFlow work for you. I see some giggles. People know what I'm talking about. There are other systems which are potentially nice, but TensorFlow is very industrial strength. It's going to debug. So I think kind of you've got to make some trade-off here. You want something that's pretty stable, if a little painful to work with, and you have to learn to kind of put up with it. TensorGraph, I think, abstracts away a lot of the TensorFlow-ness, but there is still some stuff that keeps through. So now we've kind of defined the inputs that represent the molecules of the system. The question is, how do we do the graph convolutional transformation? So one of the things that was hidden away is that GraphCon tensor graph is actually about a 10-layer deep network. So there's about 10 layers of various transformations. These GraphCon, you remember the picture I showed, there's some things called batch norm. It's a standard machine learning transformation. You have multiple other things, like you have graph pooling, you have various dense layers. So there's actually a good amount of stuff that was going on underneath the hood of that system. But it's not that bad. You can express in about 30 lines of Python. And if, let's say, you're very curious and you think, graph pooling layers are terrible. Instead, I want to double the number of graph cons I have. That's about 3-line change to the code. So you don't need to use the primitives that we provide. You can assemble, mix and match, and kind of build your own systems. So if you want to do something interesting, like some people want to say, learn to compare pairs of molecules, you can do that just fine with the system. So the nice thing is this provides a framework to kind of orient your thinking and let you kind of get off the ground and design your own systems. So now that we've kind of assembled the core of our tower, done the graph convolutional transformation, we need to get outputs out of the system. So you have this little bit of code that for every experiment that we have in our data set, it puts out a prediction. So for those of you who've done some machine learning, you'll recognize the Softmax term. So Softmax is used to make a binary prediction, a 0 or 1. You kind of assemble these Softmaxes, you get the cost. So another machine learning factoid, any machine learning system must have a cost associated with it. You take this cost and you try to minimize it on the training set. That is, you want to learn a representation that explains the data that you have in-house. And this is turned into a calculus problem. So all machine learning is, when you strip away all the nonsense, is doing very simple calculus. Here's a function, albeit complicated. Let me find the minimum of that function, and let me do so quickly on a machine that was generated to first play video games. That's the heart of deep learning. And this is kind of how you represent the cost function for the graph convolutional tensor graph. That doesn't look so bad. It's about 100 lines of Python in all to make a system that is quite sophisticated underneath the hood. And now, how do you train one of these things? There's a little bit more underneath the hood. Because there's multiple inputs going in, we need to take our data set, we need to split it out into batches. And out of each batch, we need to assemble the various bits and pieces that we use to represent the molecule. This takes a little bit doing. It's about 20 lines of code. It does take some peering, but if you kind of stare at it, you'll see there's that atom features and that degree slice and that membership and the adjacency list we mentioned up. And finally, when you do all this, you can begin to train the model. So, and when you kind of train it and then evaluate it, it comes out to, it's about the same accuracy, 80%. So the nice thing is that we gave you this kind of wrapped up, bundled up primitive that you can say, apply as a black box. But if you are a sophisticated user, you want to do something cool, and you say, I don't want to use what you gave me, I want to do something new, you can do that too. So the nice thing about the API is it exposes you the ability to build your own models. So there's some calculation on molecules that you're very passionate about that is not expressed in our pre-captured machine learning models. All it takes is a little bit of calculus, a little bit of writing, 100-line Python script, and you're kind of off to the races. And that's kind of it. I think if you're curious, I recommend checking out this Python notebook. You can run it for yourself. It will take about 5 minutes to run on a standard laptop, so it should not be hard at all. Now, one caveat, DeepChem doesn't run on Windows. If you are a Windows hacker who wants to help us fix that, please get in touch, and thank you for listening. So we're going to do one more talk, and we'll have a 5 or 10 minute break in between before the next session. Ready?
Okay, so I've got about 25 minutes to try to teach you everything you need to know about reinforcement learning to get started using it. Shouldn't be any problem, right? This will be mostly a theory talk, just describing the theory behind reinforcement learning. Hopefully, I'll have time at the end to go through a concrete example. So, what is reinforcement learning? Reinforcement learning is a method for training computers to play video games. That's what it is. And other useful tasks. Hopefully, even some chemistry-related tasks. We are hoping it will work. We're working on it. Things like folding proteins, designing molecules, designing synthetic pathways. We're hoping it'll turn out to work for these, but remains to be proven. But really, mostly it's about the video games. If you look at the reinforcement learning literature, it is full of video games. And the reason is just that they make fantastic test cases. They are very precisely controlled environments. They're completely reproducible, but at the same time, they can be just as complicated or simple as you want them to be. The logic they require can be as simple or complicated as you want. So the reinforcement learning literature is full of training computers to play video games. I would even go so far as to say that the more you can make your problem resemble a video game, the more likely you are to be successful applying reinforcement learning to it. All right, so what is reinforcement learning? How does it work? So the basic idea is that you have an agent that interacts with an environment. In the case of a video game, the agent means the player, the environment means the game. So a player interacts with a game, an agent interacts with an environment. The environment has a state and it has an action space. So the state means whatever the agent can observe about the environment. In the case of a video game, that would mean the image on the screen at some moment in time. The action space means everything that the agent can do to interact with that environment. So all the keys you're allowed to press on the keyboard, or all the positions you can put the joystick into. Basically anything that the agent is allowed to do to the environment. Depending on the environment, the action space could be either discrete or continuous. Currently, DeepChem only supports discrete action spaces. So you need to have a fixed list of discrete actions that the agent can perform. But it's possible in principle to have continuous action spaces, and hopefully we will be supporting that at some point in the future. So the agent selects one of those actions to perform at each step, and it does that by following a policy that we call pi. This is simply a conditional probability distribution. So pi means the probability of selecting action A given that the environment is currently in state S. And having chosen an action to perform, the environment then updates its state. So you pressed a key on the keyboard, or maybe chose not to press any key, and now the game has moved forward one step. The image on the screen has changed. But in addition, the environment returns a reward. So positive rewards mean that something good happened, negative rewards mean something bad happened, 0 means nothing in particular, good or bad, has happened. And your goal is simply to maximize the sum of all rewards that you earn over the entire task. So the total number of points you earn playing the game. But the rewards can often be much more indirect things. In fact, in many tasks, you simply have a 0 reward at every single step until the very end when you complete the task, and then you get a reward of 1. It makes it quite challenging to learn because you take hundreds of steps and perform hundreds of actions, and all your rewards are 0, and then you take one more action and you get a reward. Well, in some way, that reward was presumably caused by all these actions you've performed, but you don't know exactly what the connection is. This is known as the credit assignment problem. Given that you just received this reward, how do you assign credit for that reward to these actions that you've taken? And that's the fundamental problem that reinforcement learning algorithms have to solve. Okay, let me give you a few more definitions that are very important to how we formulate reinforcement learning. Usually we don't actually work with a total reward. We instead work with what we call the discounted reward, which looks just like a total reward, except we've got this extra factor of gamma in there, which is called the discount factor. So the ith action is multiplied by gamma to the I. And gamma is typically a number between 0 and 1. And this is saying that we care more about short-term rewards than long-term ones. Now, is that really true? Because don't you really care about the total reward? Well, yes. You can think of this as a bias variance trade-off. You really want to maximize the total reward, but that's the sum of a huge number of terms. Getting accurate estimates could take a huge number of repetitions, and that's very expensive to do. Whereas by putting this discount factor into it, you're saying, okay, it's mostly going to be dominated by a smaller number of steps, which means we can sample it less expensively. So this is an assumption. Whether it's a good idea or not depends on what your problem is. Think of a video game like Pong. So you're controlling a paddle, there's a ball coming towards it, you're trying to position your paddle so that you hit it back, and ideally you want to hit it back in a way that will be hard for the other player to return. That's really about as far as you look ahead. There is no long-term strategy in this game. So in a game like that, this is a very reasonable approximation. Really, you only need to think about relatively short time horizons. Contrast that with a game like chess, which is all about long-term strategy. For example, the opening is critical to the whole game. If you open badly, you're going to be at a disadvantage for the entire rest of the game. So if you were to try to use reinforcement learning to train a computer to play chess, you would probably set gamma to something very close to 1. But in any case, it's a hyperparameter. You pick it in a way that's appropriate to your problem. Next, we have this something that is called the value function or the state value function. It is the expectation of the discounted reward given that you are currently in a particular state. So this is saying, given that we're starting from this state, what do we expect our, on average, our discounted reward to be? Now notice that this depends on your policy pi, because obviously this is going to depend on what policy you're following. If you are following a good policy, say if you're a really good chess player, this will probably be a lot higher than if you're a really bad chess player. So this depends on what state you're in, but assumes you're in the state and you follow this policy. What is the expectation value of the discounted reward? And then we have a very closely related quantity called the action value function or the action state value function, which is the expectation value of R given that we are currently in this state and given that we take a particular action. So it's saying, just for this one step, forget about the policy and assume we take this one particular action. And then from then on, we follow the policy. So these are very closely related quantities, but we use them for answering different questions. V is used for saying, how good a state is this to be in? Whereas Q we use for saying, given that we are in this particular state, how good is this action to take? Okay, so how do reinforcement learning algorithms actually work? There are actually a few different approaches that get used, but here I'm describing the particular approach that is used by all of the algorithms currently implemented in DeepChem. And the idea is pretty simple. You define a policy. That is, you're defining this conditional probability distribution pi. And typically you will define that by a neural network. So you create a neural network whose input is the state and whose output is a vector of action probabilities. And then you are going to follow that policy for some number of steps. We say that you're generating a rollout of this policy. So you allow the agent to interact with the environment for some number of steps. The agent follows the policy. You collect up all the rewards. And then you're going to try to optimize the policy. And you do this in your very standard machine learning type way. You will write some sort of a loss function. You will compute the gradient of that loss function with respect to all the variables in your neural network. You will take one step of gradient descent or some related algorithm. And then you will repeat again and again and again, generating thousands, millions of rollouts. And hopefully, over time, your policy will become better and better at accomplishing this task that you're trying to train it to accomplish. Okay, what should that loss function be? Because this is a critical thing. We have a neural network, but then we have to say, what is the loss function we're trying to minimize? And it's not at all obvious what that should be. So let's think about it like this. Suppose we could treat this as a simple supervised learning problem. Suppose that at every step, there was a single unambiguous right action to choose. And furthermore, assume that we knew what that right action was. In that case, we could just treat it as a supervised learning problem, and this would be a very conventional loss function to use. Just the sum of the negative logs of the probability of A star, where A star is the correct action at every step. So this loss function, when we minimize it, all that is saying is that at every step, we want to maximize the probability that it will choose the correct action. Unfortunately, this isn't the case. Generally, there isn't a single right action, and even if there were, we wouldn't know what it was. In fact, the only thing we really know about is the action we took. So we followed the policy at every step, we took an action, and something happened. If we had taken a different action, presumably something different would have happened, but we don't know what. All we really know about is the actions we took and the rewards we got. And so we need to write a loss function that depends only on those things. So we instead use the slightly different loss function. It looks a lot like the previous one, but now we have A instead of A star. So A is the actual action that you took at every step. And now we're going to multiply that log probability by some number phi. The idea is that phi should in some way indicate how well things went. Was this a good action to take? Was it a bad action to take? If phi is positive, then this loss function will tell us that we want to reinforce that action. We want to say, if we're in that same state again, we want to increase the probability of taking that same action. If phi is negative, we want to do the opposite of saying, no, that was bad. If we're in that same state again, let's decrease the probability of taking that same action again. Okay, what should phi be? That's our loss function, but we need to pick what phi is. Well, one thing you might think is Q, which we defined before, this state action value function. Sounds like exactly what we want. Q is a measure of how good is it to take that action when you're in that state. Sounds like exactly what we want. There's only one problem, which is that we don't know Q. In fact, if we did know Q, we'd be done. We had solved our problem. Then you can basically create a, I think, even provably optimal policy by just, at every step, take whatever action has the highest Q. So unfortunately, we don't have that. Well, okay, Q is the expectation of R. The R is the discounted reward. So you might say, okay, all right, let's use R as phi. You can think of R as being an estimate of Q. After all, Q is the expectation of R. It is an unbiased estimate, and that's good. However, it could be a very high variance estimate. But nonetheless, we might hope if we just repeat this enough times, our policy will gradually converge, towards a better and better policy. And in fact, this works. This was one of the earlier algorithms developed for reinforcement learning. I believe it was introduced back in the 90s. And you can, in fact, use this method, and it does work. But it doesn't work all that well. The problem is that it's very, very sensitive to how you define your reward function. And you can understand why if you think about it like this. In many problems, a very natural way of defining your reward function is that it's always positive or zero. So when something good happens, when you make progress toward achieving your task, you get a positive reward. The rest of the time you get a zero reward, it's never negative. Well, that's a natural way to define the reward function. But if you define it that way, that means your discounted reward, R, is never negative. It's always positive. So if we use R, substitute R for phi in that loss function, that tells us that no matter what actions we take, they are always going to get reinforced. If things went well, they'll get reinforced strongly. If they went badly, they'll get reinforced weakly. But the network is never going to get a message that says, no, that was a bad thing to do, don't do that again. And so you can imagine how this can very, very easily get trapped in bad states, in bad policies. Okay, well, you might say, okay, so we just need to define our reward function more carefully. And yes, that's one way of doing it. But reward engineering is actually a pretty hard problem already. And often a much easier way of doing this is to just change the definition of your loss function. For example, let's just subtract the constant from R. Typically a small constant, and now it will be, the result can be either positive or negative. Quite well, surprisingly well, in fact. You've introduced a new hyperparameter, C, that you have to adjust, but that's not a big deal, and it does work quite a bit better than just using R. However, it is still not perfect, because in general, there will not be a single value of C that is ideal all the time in every state, in every rollout. So let's try something even better. Instead of subtracting a constant, let's subtract off the value function. Remember, that's the expectation of R given that you're in a particular state. This expression is known as the advantage function because it's basically a measure of how much better or worse did things go than you expected them to. V is the expectation value of R. So if that quantity is positive, it means you did better than you expected to. If that quantity is negative, it means things went worse than you expected it to. So you don't really care about how well you did in absolute terms, just whether you did better or worse than you expected to. If you did better than you were expecting, that means, oh, this looks like we may have taken a step in the right direction. Let's reinforce that. Let's try more of that. If we did worse than we thought we would, that means, oh, we may be going in the wrong direction. Let's try something else. So that's the basic idea of this. There's, again, just one problem. We don't know what V is. Okay, if we don't know what V is, can we approximate it? Well, neural networks are a really popular way of approximating arbitrary functions. So that's basically how many of the most successful reinforcement learning algorithms work. You actually create two neural networks, or more typically, you'll create one network with two outputs. One output gives you your vector of action probability, so your policy pi, and the other one outputs an estimate for this value function v. And then as you collect data, you will try to optimize both of these outputs at once and try to make it better and better at giving good outputs for both of those. Okay, so that is basically the theory part of this talk. So now I'm going to go through an example, and let's see, can you... Let's see, let me make this a bit bigger, just Control+. See, is that somewhat readable? So we are going to train our computer to play Pong, a very important chemistry problem. Many chemists have spent a lot of time over their careers working on this problem, as well as a lot of machine learning researchers, seriously, a lot of time. So the first thing we need to do is create a class that will represent this environment. Fortunately, we don't need to actually implement Pong ourselves because OpenAI has created this amazing project called OpenAI Gym, which is a huge library of environments that are appropriate for reinforcement learning research, which includes, among other things, a huge library of Atari games. And so we can just use their implementation of it. Furthermore, DeepChem has a class called Gym Environment that gives you a completely seamless way to use these environments from OpenAI Gym. And so we're just going to use that. We could just say, env equals gym environment, give it the name of the particular environment we wanted, we'd be done. But like Art said, we usually want to do some sort of pre-processing on our data. And so in this case, it just turns out that if we pre-process the screen image a little bit, we can make the learning problem easier. And that's why we subclassed it here and just put in this little bit of pre-processing. So we take the image, we make it a bit smaller, we convert it to black and white. Nothing fancy, but just to make the learning problem a little easier. Okay, so we've got our environment. Now the next thing we need to do is create a policy, and that means creating a neural network. So let's scroll to the right place if I can. There we go. So the way we do this is create a policy, and our policy is just defined as a series of layers that make up the neural network. And it's pretty simple how we do this, and we don't need a very complicated network. In fact, basically every line here is one layer. So we start with a couple of 2D convolutional layers to process the image. That's not very many. If we had a more graphically complex game, we would probably want significantly more than 2 convolutional layers. But Pong is a really, really graphically simple game, so that actually is enough for this. Next, we have a single dense layer, which is, you can sort of think of that as being where the main game logic is going to reside. It's just a fully connected layer, so every one of the outputs from the convolutional network is going to go into every node of the dense layer. We also stick in a quite small gated recurrent unit here. So that's a type of recurrent unit which we use when you need to include memory in a network. And Pong doesn't actually require a lot of memory, but we do need a little bit so we can keep track of how the ball is moving. If all we had was just the input state at any given moment, so just one screen image, well, we can tell from that where the ball is, but you can't tell which way it's moving. To keep track of which way the ball is moving, you need to be able to track it from one step to the next. And so this gated recurrent unit gives it just a little bit of memory so it can keep track of that. Then we concatenate the GRU and the dense layer together, and then we use that as the input to our 2 final layers. One is a layer that computes our action probabilities, and the other computes our estimate of the value function. So great, we have got our policy all put together, and now we have to say what algorithm, hyperparameters, et cetera, we're going to use. And well, we do that entirely in this one line here. We are going to use an algorithm called the asynchronous advantage actor critic, or A3C algorithm. This is one of the most widely used reinforcement learning algorithms. It's a pretty nice algorithm, and it actually has a bunch of hyperparameters that you can set, but we try to give reasonable defaults for everything. And in the case of this problem, almost all of the default values work quite nicely. The only one I found I really had to modify was the learning rate. So we give it a slightly lower than default learning rate. Okay, so we've got it. The next thing we would do is call fit on this A3C object to say, oh, yeah, run 8 million steps of fitting. This is commented out because we don't actually want to do this, because when I actually ran the fitting previously, it took about 3.5 hours on my laptop, which is not bad, but you don't want to be sitting here for 3.5 hours. So fortunately, I've already got a pre-trained model, so let's just watch it. And I'm afraid the picture of the game is going to be really, really tiny because this is a really high resolution screen and you can't resize it, but hopefully, let's just enter and then Alt-Tab. Or wait, no.
What's that?
Oh, there. Okay, you better see what's going on here. Oh, I'm sorry. That's right. We need to rerun everything. All right, just a sec.
Is your kernel restarting on all? We should get down there.
Yeah, you're right. That's a good way. Restart and run all.
Give us 30 seconds.
Oh, hopefully not even 30.
Yeah.
Sorry, it should be coming up. Here, that may have come up in another.
Nope.
No. Ah.
Okay, it's once
Oh,
up.
there it is. Okay, there it
There.
is, up in the corner. And I'm afraid it's kind of tricky. So we are the policy is controlling the green panel that's on the right. The game's built-in AI is controlling the one on the left. The game's built-in AI actually follows a totally trivial policy. It just tries to keep its paddle even with the ball at all times, which actually is a pretty good policy because it means that it's perfect aim. However, to make it possible to beat it, they put a limit on how fast it can move. So the way you beat it is to try to hit the ball in ways that where the ball gets going faster than the opposing paddle can keep up. And if you watch, you'll see that the policy has actually gotten really good at doing that. It really likes to hit it just off the corner of the paddle or hit it when it's moving really fast, and it's gotten quite good at doing that. Like, hey, it's doing really well.
Yeah.
The game ends when it reaches 21 points, so you know it's.
Question?
Yeah.
So what sort of chemistry problems do you think are most amenable to reinforcement learning?
That's a very good question. So we would love to be able to try to fold proteins. We have not yet come up with a good strategy for doing it. We have been looking into designing RNA sequences. We have been looking into designing synthetic pathways. There may be other sorts of things that it could be useful for, but
So
yes.
we have made one breakthrough. I think we've realized if we can solve a part of StarCraft, we can definitely pull proteins. So we're going to get some fun. Exactly. And so that's our next big goal, StarCraft.
Is the challenge in that, why is there a crux yet, or is it still just
Of StarCraft, you mean, or?
of something like folding proteins in this sense? Is it hard to fit it into?
It's well, okay. Folding proteins is an incredibly hard problem. People have been trying for 50 years. Yeah, basically, can we formulate that problem in a way that we would have a hope that an agent could really evolve a policy that would work? You can think of all sorts of fairly trivial ways to try to formulate protein folding as a reinforcement learning problem, but most of them we look at it and think about it for 30 seconds and say, no, there is no way it would actually learn to do it successfully. So it's just a really hard problem.
So one way to think about it is that reinforcement learning has just recently succeeded in making small robots walk. A protein is like a 50-armed robot. So consider a 50-armed blob, I don't know, abyss monster from the deep you're trying to control with a artificial intelligence. That's what protein folding is essentially. So it's much harder. The dimensionality is tremendous. We don't know the moves. In Pong, we know we can move up or down. In protein folding, what do we move and how? So it turns out to be extraordinarily complicated. And we do think this is, I think, a very powerful approach. It's just not obvious. The hope is that, if you build enough tools, eventually it'll become easier. But this is an active research problem that I think we haven't solved.
And one of the things we like about protein folding is that it actually has already been formulated as a video game. If you're familiar with Folded, it's basically a game where your goal is to fold proteins, and they've actually shown that the best humans playing this game, can actually do a better job than our best algorithms at some problems. And so we are hopeful that maybe we can train a computer to play this game or something like it.
So given it's a step-by-step function, and you don't run into don't have any issues in sort of folding?
So yeah, I mean, you mean So there's two different levels of minimization here. There is training your policy, and then there is your policy, your agent executing the policy to fold a protein or do whatever. And yes, so that second one is where I'd be more concerned about the local minima. Training the policy, machine learning, deep learning is always very finicky, but you run it enough times and tweak things enough, and you have, if it's reasonable to get to work, you probably will eventually.
So what about something like a protein marking binding, where you're just analyzing the trajectory of a known active compound with a crystal structure, and you're looking across that trajectory and maybe analyzing a descriptor like protein ligand interactions across that trajectory? Wouldn't that be a little bit easier as a starting point than protein folding?
Yeah, although what would be how would you describe that as a reinforcement learning
So
problem?
you would describe that as a reinforcement learning problem as looking at a particular state as connecting a certain amount of protein ligand interactions, and as those interactions change, if you call those different states, you do some unsupervised learning to define that. And then you would have test compound things in the dots that comes up to be the highest probability of binding, and then you would actually run those trajectories and analyze them with the validation being kind of this known active compound that have a crystal structure for it, ideally.
Yeah, it is conceivable that could work.
If you're curious, the notebook is online. We highly recommend people try that.
Yes. Oh, we won 21 to 10. So yay. Yes, I just checked into this notebook yesterday, so it is in the DeepChem repo.
I'm struggling. You were talking about doing the protein folding and that's reinforcement learning of the system, which of course we don't have for the protein. I mean, we don't. So you just pull a folded protein from a protein database and then just let it execute random.
Well, no, the goal would be that you start with an unfolded protein, not the folded one, and then you want to. So the goal would be to train an agent to be really good at folding proteins, hopefully using some of the same sorts of intuitions that the best folded players are using.
But what guides its movements, assuming you don't have
right. So one
model of how protein moves.
Right, so you would say what are the sorts of actions that it can take? Is it like moving individual atoms? Is it like torsional moves? Is it what are your moves? And then how do you describe the state? Well, you could just say like the XYZ coordinates of every atom, that probably to be useful and for it to have any chance, you'd want to incorporate a lot more information than that. Like you might want to incorporate the current potential energy of it. Possibly much more detailed information. So all these are questions that we've been thinking about in terms of how could we formulate this.
Confused by your reward.
What's the reward?
Yes.
Yes, this is one of the questions. So like for in Foldit, they use the Rosetta scoring function, and so that's what you're trying to optimize. And so in that case, you could say a very reasonable reward would be the change in the scoring function. It's one thing that we could try.
Okay.
All right, cool. Thank you, everyone. We're going to take a 5-minute break and we need to get
But it's nice. I shared it on OneDrive link with you.
Oh, wonderful.
So it might just be in your email.
Let's see if, oh, there it is.
Obviously, I don't know whether this is solving the problem because I can't be able to testify on it.
Let us see if it works out. If it does, this is looking hopeful. We enjoyed the first two talks.
Yeah, they were great. I heard someone say that in an earlier iteration of DeepChem, you guys tried to do a live demo and it would crash and BJ since told you that you're not allowed to do live demos.
Yeah, well, like you said, you have to do it right, so we practiced a lot more this time. This is looking good. Let's see if this pans out for us. It's going to be laggy. Let's give it a minute.
So the first one I didn't substitute. I'm not considering it because I thought it was non-essential. But there were a couple that were more important.
You want to just scroll through? It might be a little laggy on the edge. All right, folks. Let's get back to All right, folks, let's get back in. We're going to run out of time for next talks.
We're boosters today. It's hard to get people.
Hi, folks, come on, let's get back in. We have two more exciting talks. I want to make sure we give the speakers the time to talk about their full work. We'll have a bit more mingling time after the talks are over. I think we have till 8:30, and after that we need to be gone, but I think we should have 20 minutes after the talks to mingle more. Okay. All right, so we're now going to have a talk by Jocelyn Sincerity from Data Coast Group, talking about their work using 3D convolutional networks to understand protein ligand binding pockets. So for those of you who work in drug discovery, it's a very important problem, so I'm looking forward to hearing what Jocelyn has to say.
Hi, I'm Jocelyn, a third-year PhD student working with David Coase. His background is actually in compiler optimization, but now he has an appointment doing computational and systems biology. And our main project right now is called Nina, in the new naming style, it's a reference to Autodog Nina, so GNU is not Nina. It's a free and open source program that started off as a fork of Autodog Nina, but now it supports things like scoring using convolutional neural nets, and we provide some pre-trained models for doing that. It's still very much in development stages, but if you'd like to use it for that kind of thing, you can definitely use it or contribute. And also, hopefully, some of the methods that I talk about here will be useful or provide commentary that we can discuss later. So I'm going to start on the problem, and then I'm going to talk about how we developed our CNN approach, and then talk about some perspective stuff that either we're working on or thinking about working on down the road. So I'm assuming that probably most people are pretty familiar with the major problems in structure-based drug design, but two major tasks are virtual screening and lead optimization, and sub-problems associated with these tasks are predicting the pose, so predicting like how the atoms are oriented with respect to each other in the different molecules. And then also you could treat it as a binary classification problem and say, okay, which things bind strongly versus which don't. And also we could care about being more precise about predicting the affinity. And then if we're able to do those tasks accurately, something that we would like to do if we have a good model or a comprehensive model is to say which parts of this interaction are not working well. Which things are preventing us from having strong binding as we could, and then how can we optimize? So how can we optimize the compounds that we identified to improve binding? So those are things that we want to be able to do to improve drug development. And so in particular, taking a static image of a protein and ligand interacting with each other, let's associate a score with that to try to get at which components of the interaction have which properties. And so I have other Vina here as kind of an example, but one of the past ways of doing this was to have pairwise potentials, and you have a weighted sum of terms that were chosen because they are chemically important. So they might be chosen a priori, things like steric terms, hydrophobic, hydrogen bond terms, things that we know are relevant for binding ahead of time, and then we assign weights. Maybe they are distance dependent, or they depend on the atom types of the pair of atoms that are involved in a particular interaction. But one thing that is limiting about this is that often the terms are chosen ahead of time. Maybe manually by an experimenter or someone who's developing the scoring function. And obviously, it's probably unsurprising that I'm going to say we can probably improve on this, and it's also probably unfair to just look at Vina and a recent improvement on it in 2016, Bernardo, and say this is the state of the art. But in general, if we look at performance on these various tasks, it's definitely a problem that we can still improve upon. We're not doing perfectly or anywhere close to perfect. So obviously, because we're at the DeepChem talk, I'm probably going to say deep learning is the solution. But here we have a lot of data available, and it's very attractive in this problem that has a lot of spatial features that determine how strongly these things interact, that we would want to leverage that data that we have. We have annotated complexes. Even if we try to be very picky about the quality of the complexes, we still have thousands and thousands of annotated complexes that we can use for training. So that becomes a nice way for us to try to improve on the state of the art. So that's exactly what we tried to do, and motivated by the success of convolutional neural networks in image classification, we thought about this as a naturally generalizing this approach to structure-based drug design. And specifically with CNNs, a couple of the features that we find attractive are, one, being able to identify local structure that's important to classifying something. So that's something that we think is important for protein ligand binding. There are obviously local features of an interaction that are the things that together make an interaction one that's strong, or one that is representative of a high quality drug. And also there are things like weight sharing across the filters that make the models, regularized, easier to train in some cases, and less prone to overfitting. So those are some of the things that attracted us to this approach in the first place. And now I'm going to talk, specifically about how we've designed our model, and how we trained it, how we optimized it, and then how we evaluate it, including how we visualize what it's learned. So if you're looking at an image, obviously you have these two spatial dimensions, and you have the RGB channels indicating the colors. We generalize this to three spatial dimensions, for voxels that have atom types associated with them. So this allows us to be really minimal in the overt featurization that we do. Instead of having to pick out specific chemical features that we think are important ahead of time, all we have to do is decide how close we want the grid spacing to be, how we're going to represent atom densities, and what atom types we're going to use. And as it turns out, for some of those things, the model is not even very sensitive to those things that we select, specifically for atom types. So this will end up being more important later, but we wanted to have a continuous representation of the atom density. So we're Gaussian out to the atomic radius, and then we become quadratic so that it decays to 0. And this, for a given grid point, gives some information about how far away atoms are based on the amount of density that is at that grid point for that atom. We actually also have used, for example, a Boolean representation, but this doesn't give us the same level of information in terms of how far away the atom is, for example. And it also has discontinuities that are not amenable to obtaining gradients that we want to use later. And I'll get into more.
What about electron density?
Sorry, electron density? That's a separate thing that we actually also want to do. But yeah, right now, this doesn't include that. We want to do electron density very much. The main thing that's important here is that we have different types for the receptor. These are kind of just standard atom types.
What is the difference between atom density and electron density?
Here we're just saying, we have some representation of a van der Waals radius, so we know that, much of the atom is here, and then we just want something that indicates how far away it is. But the electron density would have a a shape that would be different.
But what is the property of the electron?
Yeah, those are related to each other, but I don't think this contains all of the information that electron density does. So we don't want to claim that that's what it is.
The crystal structures are created from the electron density.
Yeah, but it's not trivial to convert the electron densities in a crystal structure into like a 3D Box-Loy structure like this.
Yeah.
It's really not a trivial problem.
I don't know about that. We should talk about that after.
Sure. You got a Python program.
Reminder, there's mingling time after. Questions after, please.
Okay, so if we have three major tasks, we have a couple of different data sets that we use for training and testing. For pose prediction, we use both CSAR and PPBind. I guess the main critical thing here, one thing is CSAR is much smaller than PPBind is, but I'll go a little bit later. Additionally, we don't just use the crystal poses because, for example, for the D-quiz, we don't have crystal pose, and we don't want the classifier to learn to distinguish between experimental structures and things that are computer generated. So we generate all of the poses, we do computer generated poses for all of them. And for the actives, we keep things that are within a threshold RNC from the crystal pose, so that we avoid learning a signal that isn't the signal we want to learn. We have done binding discrimination of things besides dude. I think they're not recommend using that, but here we don't have any true poses, so we have to use the docked poses as the true pose. And affinity prediction, again, we use PPBind. And we also do clustered cross-validation. The cutoffs for CSAR versus PPBind are slightly different because the CSAR ones came that way from the CSAR set. But anyway, the idea is just there is a large amount of redundancy in proteins that are available, and we don't want to accidentally be testing on train. So we cluster based on protein similarity. We actually did both sequence and structural similarity, and we hold a part of the set out to train on and then test on the rest, and do this for each of the different folds. So how do we, oh right, data augmentation, sorry. I had to convert these videos, there it goes. So one thing is that CNNs are not rotationally equivariant, so we have to handle this somehow. Ideally, you would incorporate some kind of equivariance into your model architecture. Rather than doing that, a standard thing to do is to do data augmentation and to incorporate random rotations of your input. And basically then your network sees the same thing rotated and it sees the same label, and so it is in effect learning probably the same filter rotated. So this is wasting some of your model capacity, and you don't have any guarantees about actually like approximating equivariance, but we find in practice that it seems to work well, and it's a pretty standard method for like dealing with the fact that the representation is different depending on whether on the rotation applied to the input. And here you can see that for when we don't have the augmentation, the train obviously is overfitting, and then we see a huge drop off in performance on the test. And when we incorporate this data augmentation, we don't see the same level of overfitting or drop off in performance. So this is by default applied to our inputs. And I should say also that we are using Café, and we have a custom gridding layer that incorporates like a guide blow-off exclusive scan kind of trick for doing gridding very quickly. And this is done on the fly. So we had a model optimization procedure where we started off with sort of a literature-inspired model, and then tried varying certain parameters, and ultimately came to the model on your right. And it isn't extremely deep, but that ends up being nice for us for performance. And I think one thing that we think is that when it's less deep, we're less likely to overfit. And we also have a visualization routine so that after we have a trained model, we can see what it thinks are important. So here on the left, the coloring is just like a typical element coloring. And then on the right, the coloring is according to the score that the model is giving. So red is bad and green is good. And basically it's just an iterative deletion method where we see how the score changes when parts of the molecules are removed. Either residues for the receptor or atoms and then fragments for the ligand. And we can use this, it's useful, one, to get an idea for like what the model thinks is a good or bad thing about a particular interaction, although obviously we can't like at least at this stage we aren't attributing that a particular part of the tree. And it also could be useful, for example, if we're going to approach a medicinal chemist and try to argue to them that this is a good target, or a good, sorry, compound. We can say these parts of the interaction are favorable. So this is some results from cross-validation. This is just an AUC curve. You can see comparing to Vina, and then these are two other Norman and then a random forest method that are in the literature. We do well, but this is not actually a task that people care about because this is looking at all targets at once and just ranking low RMC poses first. What you actually care about is the second thing, and that is intra-target ranking, and this looks less good, obviously, on this round. But
Can you explain the difference in intro versus?
this is all targets together, just saying, like, let me rank the low RMSD poses earlier. So, like, any active, any low RMSD pose. This is going against individual targets and saying, did I find, is my top one ranked pose an active or not? In the top three, do I have an active, meaning something that's within, in this case, 2 RMSD of the crystal pose? And then the percent is saying, for how many targets did we successfully do that?
And Vina generated the post both times?
Yes. Yeah. So here, right, I was going to say, this is a problem that can be cured with more data, as it turns out. So P-Divine is a larger set, and it turns out that even for intra-target ranking now, if we are training on more data, we outperform Vina, even on intra-target ranking as well, after I said that. And we found that it's surely a function of the amount of data that we have to train on. So if we reduce this down to like the same, it's a P-Divine data, but we reduce the amount that we train on, we start to have degraded performance again. So it appears that we're just having more data, and that's a promising sign, maybe, in that there's more data being created all the time. I'm not going to spend too much time on these results figures. That's just finding a classification problem on Dude. This is kind of interesting. We have some poses that are partially aligned to true poses. So the magenta is a true pose. And then the other poses have been selected because they are aligned on part of the compound, but another part of the compound is not. And then we use our visualization method to see what parts of the compounds pose the model likes, the CNN model likes. And it is liking the part that is aligned to the correct pose. So that's promising for us too, and it's not, in general, liking the part that is misaligned.
So what's the definition of liking?
The green means that those things are having a favorable impact on the score. When we remove them, the score goes down significantly. And dislike is if we remove it, the score goes up. So it's having a negative impact on the score. Our affinity prediction model is still sort of in early stages of being trained. Here we can see it's doing better than Vina, but there is a following evaluation where you can see we still have some work to do. We compared to the ACNN model from you guys and the splits from your paper. So anyway, this is not so easy to see. This is a little bit better, and you can see that we are not beating you guys yet. But everyone's having a hard time with the scaffold split, and currently our theory is that it's been truncated.
Is that a P-Divine for 5?
Yeah.
Okay, cool.
And so then the next thing is, okay, obviously we still are working on things like the affinity model, but how can we extend what this can do? So a big thing we want to do is generate more poses. Right now, I think like somebody mentioned, we're like generating poses with Vina, for example, or using some other method, and then rescoring those. So we want to be able to generate the poses ourselves. And in general, we just need to have some gradients, and then like the rest of our package can do a minimization, or it can do docking with a Monte Carlo method that then applies the minimization routine. And so we have this continuous representation going from the input to the output. We have these densities. And so in fact, the arrow should have extended, but I guess that animation isn't working. The point is that we can use back propagation all the way back onto the grid, as well as onto the atom centers to get gradients on the atom centers. So we do that. This is just looking at the grid and saying, okay, we can say, you know, the conventional back propagation is telling you what changes you need to make to improve your score, improve the output, you know, reduce the loss. Here we're saying, how can we change the input actually improve the score. So here we can say the model thinks that we should have more oxygen at this location and less over there. But we can also get gradients on the atoms themselves that are input. This one might be tricky. This should show you, yeah, okay. So this is like an early stage minimization video. And the thing is, at this stage, the model hasn't seen a variety of examples that are like non-physical. So we've just shown it stuff that like a standard, like would output as a plausible pose. But there are all kinds of things like actually having the compound overlap the receptor surface that you just would not see what you normally generated. And the model hasn't seen it, so it doesn't know how to do it. And I think like part of what it's doing is just trying to get like unlike charges close to each other. And so here it's just moving them as close as it can. Not as close as it can, but very close. And here the back should be showing, zoom in, showing exactly that. That the interactions that it likes, it just tried to move very close to each other, and here it gets overlapping. But I can't, it's underneath that video, I guess. So the thing is, that's actually not bad for us, because that is amenable to an iterative training routine where we say, this is where the model is confidently wrong. Now we retrain it by giving it those same things that it generated and say, these are actually bad, and then do the whole process again. And as it's confidently wrong, we show those examples to it and retrain it to recognize that those examples are no longer good. Here we started off with true poses that we applied a random perturbation to, and we kept things that were around like 4 RMSD away from the true pose, and then we give it as input to the minimization routine for the CNN. And you can see we're gradually improving, although right now it's like peaked around 0. But we're slowly getting more things that are appearing, like that are being moved closer to the true pose. So anyway, that's our current strategy for improving minimization. We also want to do compound generation. Like I said, we have this way of looking at the grids and saying, this is what we'd like to have here. And so we'd like to use that for optimization. And in general, he's not going to play without a click. It probably doesn't matter. Okay. In general, there are a couple of things that we'd like to have in a grid model. So one of those things is that we want to do as little overt featurization as possible, and we'd like to retain as much information about the spatial relationships between the atoms and the molecules as possible. So for example, we don't necessarily want to have an approach where we just look, for example, at distances. We'd like to say, we'd like to have things like bond angle information available, at least in the inputs, since it's there. So that's something that was attractive about having an approach that retains the full 3-dimensional spatial relationships in the input. Another thing we'd like to have is have a model that's size extensive. That's something that we don't currently have. I didn't say this at the beginning, but we train with a specific size grid. We can't generalize to a larger grid. We can train with a really, really big grid in the expectation that we might see something that's really large, but that's not very efficient. So we'd like something that can generalize to an arbitrary size input. We also want to be able to do optimization, so obviously we need something that we can get those kinds of gradients from. And finally, we'd like to be equivariant system symmetry. That's again something that we have been addressing with data augmentation. There are people who have talked about incorporating layers that have this kind of equivariance built in as a way of baking it into your model architecture so you don't waste time and parameters learning stuff that you already have learned, and learning the same thing rotated by some amount. So those are things that we'd like. And one thing that we thought about going forward is, since we want to generalize to arbitrary size inputs, and we like our gridded approach, at least for now, that we'd like to use RNNs. So probably you've seen this before, but the idea is that if you have a sequence, like a sentence, where like some later value depends on the things that you've seen before, you can use an RNN to represent the dependencies of the sequence of things that you've observed, and then have sort of a running history, like memory of what you've seen before, to encode that. So we have sort of 2 ways that we could go about incorporating this into the kind of model we have. One would be an atom-centered approach, where the recurrence would be over the atoms. animated this, but it's probably pretty intuitive. But anyway, I guess you saw that. And then this idea is probably the one that we're going to try first, which is doing a series of spherical shells. And the recurrence would be over the spheres of larger radius. And we would evaluate convolutions on the surface of those spheres. And I guess there are two things that we have to worry about in implementing that. One thing, I'm not sure if it's lagging. Okay, one thing is that obviously as we increase the radius of the sphere, we increase the surface area, so we need more points to maintain the density, to maintain the grid spacing, which is part of what we care about as a feature. And so I'm illustrating that, but this isn't really a problem for us in the beginning. We can pre-compute these points, we know where they're going to be located, and if we use a standard method like recursive subdivision of an icosahedron, we have a pretty elegant way of representing where these points are and their relationships to each other. So that isn't such a problem, but it also means that we will have to interpolate the hidden layer because as we increase the dimensionality, we'll be working with a hidden layer from the inner sphere from where we are now. So it won't have the right dimensions and we'll have to interpolate that. So those are the main points. This is most of our group. And here we go. That's fun.
So let's save questions for after the next talk. And we have Brian. Let's thank Jocelyn one more time for a wonderful talk. Oh, sorry. 1 second. Let me hit. All right, so our final speaker for the night is Brian Naughton of Hexagon Bio, formerly of 23andMe. He's going to talk to us less about chemistry, which is what you've heard, and of course Pong, which is a subfield of chemistry, but more about kind of biology. As everyone who's done drug discovery knows, biology is often what trips you. Chemistry can be solved, biology often can't. So I'll let Brian take it away from there.
Thanks. The background of this talk is I met Art, and he said you should talk about biology for drug discovery, and I said, okay. So that's what I'm attempting to do here. I call it a survey, but you could also think of it as a grab bag of stuff. So this is sort of a model of drug discovery, drug development that appeals to me. It's not comprehensive, but you can think of different types of therapies on the right. You can have protein therapies, nucleotide-based therapies, and then small molecule or chemical therapies. And if you sort of look at the world that way, then it turns out that almost everything is sort of bio-related, and only a small subset is really chemistry, right? Because even the biologically derived small molecules come from bacteria or whatever. You need to look at the gene sequence to really get those out. So again, a sort of curtailed version of drug development you could think of as first thinking of a target and validating it. And there are sort of very biological elements to that. Then developing your therapy. Obviously, you could develop a chemical therapy, but I'm just going to talk about protein-based therapies and nucleotide-based therapies. And then you need to test your therapy, right? You need to make sure it works, but I won't talk about that at all. So first of all, target validation. How might you do that? Well, an interesting way to do that is with human genetics. So that's my background. You can think about, this is a George Church slide, which is why it's about extraterrestrials. But what it's really saying is, if you can find someone who's double null for a weird mutation, so let's say you've got no copies of PCSK9, sort of the most famous example, then what happens is you have an extremely low LDL. In a specific example, the person's LDL is 14. So this person has no working copies of PCSK9, has a superpower called low coronary artery disease. That means that you could make a drug that completely knocks down PCSK9, and it would be a brilliant drug. And you know that because you have a person who's been on the drug their whole life, in effect. And that's what happened. And actually, they went from nothing to drug in about 10 years, and 2 PCSK9 antibodies were in the market last year. So this is sort of like the new world of human genetics applied to drug development. Find these like superheroes, as some papers have called them, and then that's your drug target. So it's a very simple model, but it's generating a lot of interest from groups like Regeneron and other pharma companies. So we want to find a double null person. We want to find one of these sort of superheroes who has no working copies of the gene. Well, there's a lot of really interesting resources to do that. So the first one is called Nomad. It's out of the Broad Institute. You go there, it will just tell you for any mutation or SNP that you're interested in, what's the frequency of that SNP in a lot of populations. It's kind of just a combination of all the data that's out there in one big publicly available database. So it's really nice. The next one is UK Biobank, which is a really incredible thing they have going on in the UK. I went to visit it one time. It was pretty wild. They had people between the ages of like 45 and 70 just coming through, getting an exercise bike, and getting a hearing tested, and getting like some people get MRIs, and they just all the data is in one giant database that's pretty much publicly accessible. You do have to like apply with the research program, but it's all there if you want it. They just added 500,000 people's genotype data, which is pretty amazing, right? And then this just launched, I think, a week or two ago, Biobank Engine out of Stanford, where they just take a bunch of data from this, run the association studies, and then put all the data available online. So if you're looking for like a new target, this would be, I think, a pretty good place to start. And then if you want to go a little bit deeper, then you could go to a biobank like Vanderbilt and say, hey, I have an idea. I want to, search for a new drug target. I need access to a specific blood sample. So you can actually set up collaboration with Vanderbilt or other biobanks and get access to data and or samples that way. And then once you have your drug target, you might say, well, how do I figure out what kind of drug target this is? So you can go to opentargets.org, which is a really cool resource out of the UK. I think GSK is involved. And they'll give you, for any gene you're interested in this case, it's PCSK9, the low LDL gene that I mentioned. We'll give you just a bunch of data about animal models, genetic associations, all kinds of stuff, RNA, like gene expression. So you can take all that data, try and make sense of it. It'll try and highlight computational problems that are interesting related to what I'm talking about, in case there are deep learning applications or whatever. But basically, you can use these data to try and figure out, is your drug target good? That's sort of the crux of it. Is it a good drug target? How would I maybe repurpose a drug for this that targets this gene for another disease based on these data? That would be another thing you could do. The second way that you could do target validation is with a CRISPR or RNAi screens. This is a pretty simple method that relies on the existence of RNAi of CRISPR. Essentially, you might have a dish of cancer cells. Let's say, it's some cell line that you know its properties. Then you apply RNAi to every gene. In this specific example, which is a paper that was published just a week or two ago, there's 8,000 genes. So you knock down each of these genes one at a time. You use 1 billion plates, I think. This is Novartis. They use, I think they're like in several basketball fields worth of plates or something like that. And then whichever gene you knock down, you measure to see, does the cancer grow or not? And that's it. So you can imagine, right, if you didn't know about the existence of some great drug target, like, I don't know, EGFR or something, you'd see that certain cancers are very sensitive to RNAi knockdowns or CRISPR knockdowns of EGFR, and then you could use that as a platform to start developing a drug against that target. So that'd be another thing you do. And here the computational problem is essentially taking the data and, data that kind of looks like this. So here on the x-axis, they're just cell lines. So again, 8,000 cell lines, I think, is that right? No, sorry, 400 cell lines, 8,000 genes. And then the score for each one for a specific gene knockdown. So there's loads of data, and Novartis put all the data online, which is kind of great, and a shiny app called Oncology NIBR. So you can find that online. Okay, so now we've chosen our drug target, and we want to make a therapy against it. How would we do that? Well, one way to do it is bioprospecting. So bioprospecting means you sort of go out and try and find medicines in the natural world. So a lot of medicines come from nature, right? Penicillin comes from fungi. Taxol, the cancer drug, comes from yew tree. Lots of antibiotics and other drugs come from bacteria. So it's a easy way to do it. You can also do bioprospecting in humans, right? Because humans make antibodies. So those antibodies are good drugs. You can mine the human immune repertoire for drugs. So which is also an example of bioprospecting. So this is a huge field, obviously, and this is what Hexagon Bio works on. But you can think of like lots of different computational problems related to this because it's really trying to figure out how to go from gene sequence or RNA sequence to, inferences about its drug-like properties. So you have to like infer if the gene is biosynthetic, what might the chemical be that the gene makes, is the gene annotated correctly? That's certainly important. And then if you're doing antibody mining or immune repertoire mining, you have to figure out what is this immune repertoire sequence, like antibody sequence or TCR sequence, actually going to bind. So it's like another huge problem to figure out. So if you can't find your drug in nature, then you might want to engineer your drug, right? You might want to design it yourself, which might have some advantages. It's also very hard. And I think a lot of this has been driven by synthetic biology, because that's the way you might design a protein or nucleotide-based drug. And the price of printing DNA is decreasing. It's not decreasing as fast as the blue line, which is DNA sequencing, which obviously is incredibly surpassing Moore's law by an incredible amount, but it is coming down pretty fast. And you can see things like this tweet from Twist Biosciences where they said, buy 10 megabases of DNA, get 10 megabases free. So this is sort of like almost futuristic stuff, like buying 10 megabases of DNA was like not something people talked about even a couple of years ago.
Did they say which 10 they're going to give you?
It's always random. You can find it in your bathroom sink. So let's say we want to do a therapy development. We're going to do it using proteins. So that's what we want to build our therapy from. So probably the most common type of biological therapy or biologic is an antibody, right? So you can see in the middle here is the regular human antibody. It's a constant at the bottom, and then it has two arms that vary, and the variation in their sequence allows them to bind different epitopes. But there are lots of other different types of antibody-like molecules. So I just kind of like the way that the camel and shark are relevant here, because they have single domain antibodies. It's pretty cool. Called or nanobodies, depending on who's talking about it. But then you also have antibody fragments, which is essentially just taking, the top part of the human antibody. And that works slightly different, but it's very similar. It's very amenable to like production of bacteria and stuff like that. And then another example, which is pretty recent and very exciting, is called a BiTE, or bispecific T-cell engager. So that on one end essentially has an antibody fragment that binds something expressed on the tumor cell that is unique to the tumor cell. On the other side, you have something that just binds something that's unique to a T cell. So using the BiTE, you're sort of bringing the T cell and the cancer together, and that way you get the T cell to, help the other cell eat the tumor cell. And this seems to work very well, similar to the CAR T stuff that you may have heard about in the news. So that's antibodies. They're very big, but there's another thing that's a lot like antibodies called the T cell receptor. So T cell receptors are very analogous to antibodies, except they not only bind a specific epitope, but they bind it as it's being presented by something called MHC. So this is like a regular human cell, and then the MHC is presenting this peptide, which might be like a virus that's integrated inside the cell or something like that. And then the T cell receptor comes in and tries to recognize that peptide as something that's non-cell. So again, very analogous to antibodies, but there are a lot of interesting computational problems associated with this, like predicting which peptides would bind which MHC alleles, predicting the T cell receptor binding the MHC, the epitopes, which epitopes would be produced by proteins, and then which antibodies would bind which epitopes, and so on. There's just all different permutations that are problems that are unsolved and that would be extremely useful for drug development. And partially the reason I wanted to bring up MHC is because there's this really interesting resource, immuneepitope.org, where they do this leaderboard of just algorithms that are being applied to, in this case, MHC peptide binding, I think. And it just ranks all the algorithms here. But the cool thing about this is that you can submit your algorithm by just having a little server that responds to HTTP requests that look like this. So you supply the sequence and the HLA or MHC allele, and then you give back your prediction. If you make your server do that, then it'll appear in the leaderboard. And you can also use their data to submit your query this way, and they'll give you back an answer as well. So it's kind of a cool setup, and very amenable to like experimentation with new machine learning methods. So if you let's say don't want to use an antibody T cell receptor, then you can go a little bit broader than that. You can decide to just make your own protein, right, from scratch. You just want to design your own proteins. This is a website called Seravani. The author of the website is here, Justin. And essentially what it allows you to do is sort of drag and drop all of these different domains or modules of protein to construct a new hybrid or chimeric protein with some function. And this is an interesting example. It's a CAR, or chimeric antigen receptor. And I don't know if this one is on the market or in clinical trials, but basically on this end, it's an antibody fragment that binds B cells. And on this end, it's being expressed in a T cell. So when this T cell sees a B cell that's expressed in CD19, then it gets activated. So this is what you might have heard of as CAR or CAR T, these cells that are excellent drugs. And then final example, which goes even a little bit further from antibody, is this example from iGEM 2008, the Slovenian entry. That was super cool. Basically what they did was just make a hybrid protein that is a combination of H. pylori flagellum and E. coli flagellum. So H. pylori is the bug that gives you stomach ulcers. Your body doesn't recognize H. pylori flagellum, which is why it lives in your gut. But if you make something that's half H. pylori and half E. coli, then your body will recognize the E. coli part and respond to it, but it will make antibodies against the H. pylori part. So it's a cool vaccine against H. pylori that works in mice, and I don't think they ever followed it up in humans. That would, as long as we cure these mice, that's the important thing. So the final part of this talk is about nucleotides, so DNA and RNA. The most drug-like nucleotide therapy is probably RNA, and there are some really interesting new developments here that I think are pretty exciting. So antisense RNA didn't get a lot of love for a long time, but in the recent past, 2 drugs have been approved using antisense RNA technology. One for Crohn's, and the reason it works well is because Crohn's is in your gut, so you can get RNA to your gut pretty easily, or fairly easily. And the other one's for SMA, which is a very, very serious genetic disease. And in that case, you inject the RNA straight into the CSF. So here, you can kind of see a little tiny bit here. The antisense RNA binds next to exon 7 and SMN2, and that stops exon skipping of 7 exon, and that leads to the full end transcript, which ameliorates the disease. It's pretty simple, but it seems to work and has been approved. Other RNAi, like RNA-related modalities, would be RNAi, which a company called Alnylam is working on, and mRNA, which a local company, Moderna, is working on. These are very much like, you give this just like a drug, and it does that. It's not like a gene editing technology. It's more like a drug. So the analog for nucleotides like antibodies would be aptamers. These are made of DNA or RNA. And basically the idea is you make some DNA, you see if it binds the thing you're interested in, you wash it, so you get rid of all the stuff that doesn't bind, and then you amplify the stuff that does bind, and you go around and around and around increasing affinity using one of various methods like selects or this NPPD method. At the top, you can see an aptamer that's actually approved for wet AMD. So you inject it directly into your eye. But it's pretty cool because you can literally see the sequence of the drug. It's just 30 or 40 nucleotides plus this pegylated part again. But it's the only approved drug of this kind. And then there are lots of computational problems related to RNA. So you can imagine folding of RNA, aptamer binding, just like antibody binding, et cetera, et cetera. And a lot of this stuff is sort of not untouched, but it's very early days. Lots of machine learning stuff has not been tried on this. And almost finally, DNA CAD, if you don't even care about using DNA the way it's supposed to be used, you can just make structures, which is kind of cool. Hasn't been hot for a while, but I'm still hopeful it'll come back. So on the far right, you can see cool pictures where they made a little man and a little bunny. And then at the bottom of the electron micrograph, actually, you can sort of see there's a man and a bunny shape. So you can literally make out of these almost like Lego-like blocks any structure you want. And then the purported utility of that might be that you can make a box that responds to some epitope or something, and then it would open, and then the drug would be released. And I really hope that one day that works. But it's cool. And very, very finally, I just want to sort of put a plug into self-free systems, because I feel like this is almost like where DNA or biology and chemistry meet, in that you don't need to be growing up organisms, right? You can just get someone else to grow up your organisms, burst them, take all the good stuff out of them, and put it in a tube. And then if you add DNA to this cell-free system, then it will start expressing the protein or doing whatever you want to do inside the tube. And that allows you to do a lot of iteration, which is really good for machine learning and, just like synthetic biology in general, doing things faster, iterating. But it's also somehow taking biological toolkit out of biology labs and bringing it into like other labs, just making it more accessible. So I'm also excited about that. And there are lots of companies working on that, including local ones. And that's it. Hopefully I was in time. Thanks.
All right. Are there any last questions for either Jocelyn or Brian? If not, let's give a round of applause to George out there, but we should all thank him for hosting us, for coming, and Crystal again for setting up and. All right, thank you all. That's all for today.
Yeah, you gave an awesome talk.
Since you're getting approved, which is kind of crazy to me.
Right. It is definitely a kind of a.